Someone once said that there are 10 kinds of people in the world: those who understand binary and those who don't. By the end of this tutorial, you'll be among the group that understands binary, and you'll also get the joke. More importantly, this tutorial will give you a better understanding of how modern computers work. The smallest unit of data in a computer is the bit. The word bit is short for binary digit. Like a light bulb, a bit could be one of two states, on or off. In computing, a bit represents a single on or off signal inside of an electrical circuit. These on or off values are represented by the numbers 1 and 0 respectively. From these simple bits, computers string together large sequences of ones and zeros to represent complex data and instructions. A string of 8 bits is referred to as a byte. Byte is short for binary term. Since these on or off signals are composed of finite states, we call them digital. By contrast, an analog system would cover a range of virtually infinite points. Visually, we could represent digital signals as step functions and analog signals as continuous waves. For example, in a digital computer, we can represent music as a series of bits in an MP3 file. In an analog system, we can represent music as a pattern of waves. Old-fashioned vinyl records are a good example of an analog recording medium. Rather than represent music through a series of bits, the grooves in a vinyl record approximate the actual sound waves that have been recorded. So now that we know what bits are, let's learn how such a simple system can store such a wide array of information. We will now learn how to represent virtually any number using just ones and zeros. Let's use light bulbs to represent bits. Suppose we have an array of 4 light bulbs. When a light bulb is on, we can represent that on state as the digit 1. Conversely, we can represent the off state as the digit 0. Suppose each bulb represents a power of 2 when turned on. The rightmost bulb is 2 to the power of 0, which is 1. The next bulb over is 2 to the power of 1, which is 2. The next bulb after that is 2 to the power of 2, which is 4. And finally, the leftmost bit will represent 2 to the power of 3, which is 8. When all 4 light bulbs are on, we can add up their values to get the number 15. Since 8 plus 4 plus 2 plus 1 is 15. When a bulb is on, we can imagine that we are multiplying the power of 2 by 1. When the light bulb is off, we multiply that power of 2 by 0. So if all of the light bulbs are turned off, we get 0 times 8 plus 0 times 4 plus 0 times 2 plus 0 times 1. In a moment, I will show you how to count from 0 to 15 in binary. First, I'll flash the entire process in fast motion. Then I'll break it down step by step. Here goes the fast motion counting. Now let's break it down and start at 0 with all the lights off. To represent the value 1, we turn on the rightmost bit. What we have is 1 times 1. To represent the value 2, we turn on the second bit only. What we have is 1 times 2 plus 0 times 1. To represent the value 3, we turn on the first 2 bits. What we now have is 1 times 2 plus 1 times 1. To represent the value 4, we turn on the third bulb only. What we have now is 1 times 4 plus 0 times 2 plus 0 times 1, so just 4. To represent the value 5, we add 1 times 4 plus 0 times 2 plus 1 times 1, so it's 4 plus 1. To represent 6, we add 1 times 4 plus 1 times 2 plus 0 times 1. So we have 4 plus 2. To represent the value 7, we add up 1 times 4 plus 1 times 2 plus 1 times 1, so 3 ones. Or in base 2, 7. You might be recognizing a pattern. To get the value 8, we turn on the fourth bulb only. This gives us 1 times 8 plus 0 times 4 plus 0 times 2 plus 0 times 1. To represent 9, we write 1001 in binary. It's 8 plus 1. To represent 10, we write 1010. You may have noticed a relationship between the number of bits and the number of values that can be represented. As a general rule, x number of bits can represent a total of 2 to the x different values. Let's start with 1 bit. As we know from our definition of a bit, a single bit can represent a total of 2 different values, 0 or 1. With 2 bits, we can represent 4 different values, namely 0 through 3. With 3 bits, we can represent 8 different values, 0 through 7. And with 4 bits, we can represent 16 different values, 0 through 15. In this tutorial, we defined what is a bit and how it can be used to store numbers. We learned to count in binary from 0 to 15. And finally, we noted the relationship between the number of bits and the number of values that can be represented by these bits. For more information and lots more interesting content, please check out my blog, Pumpkin Programmer, by clicking on the link in the video description. Thanks for watching.